Really casual stable around or?
No, I'm just gonna come around and get it.
Okay.
All right. And yeah, if you don't mind just like kind of reminding them what the problem is about.
Okay, I can reread the problem.
Yeah. So Sarah is going to remind you what problem 35 is about.
Hello, I'm almost here. Let's go! Just need us one more sense. Alright, I have it in my special homework folder. Alright. Just kidding. You see this, and then do this.
Yeah, because
Alright, ladies and gentlemen, 35 is up here.
Okay.
Oh, I like the pen.
Oh, thank you.
I like it. You can what?
Okay, so for problem 35, the problem was. Oh wait. I was very uncomfortable. Okay, so for 35, the problem was from 1997 to 2002, the number n in millions of DVD players sold in the United States can be modeled by the equation n equals 0.42 times 2.47 to the t power, where t is the number of years since 1997. And then part A was identify the initial amount growth factor and the annual percent increase, and then part B was just figuring out the a number of DVD players sold in 2001. So for the percent increase, since that part of the equation would be equal to 247, you'd have to do 1 plus 147, and then 1.47, and then you'd have to multiply that by 100 to get the percent, so it would be 147%. The initial amount would be 0.42 million, or 420,000, and then the growth factor would be 2.47. And then for part B, you would just plug that into your calculator because there were 4 years between 1997 and 2001, and then there were 15.6 million DVD players sold in 2001. Thank you, Anthony.
Any questions?
Oh!
Oh.
Thank you.
No?
Thank you.
Nice job.
Good job, Sarah.
So Kai has 37.
See, now it's all bubble. Look what you did. And she like cried for her mom. I was like, can you take a joke? It's funny actually. It was so funny. I laughed.
Do I have to read the problem?
Do you just want to read just like a little bit?
Okay. Wait, do I read like all of that or just the problem?
You just read the problem. Hey, ladies and gentlemen, the talking has to stop. Please.
Okay, for A it says read a model giving the population P in thousands of Austin T years after 1990. What was the population in 2000? So you have to have that, and then you plug in 2,200. Wait, am I reading it? Oh, wait, I was reading the wrong problem.
It's okay, Tom. It's okay.
So 37, it's your deposit $2,200 in a bank account. Find the balance after 4 years for each of the situations described below. So A, it's the account pays 3% annual interest compounded quarterly. So you plug in 2,200 for A, and 3% is the R, and you plug it in there, and it's quarterly, so you divide that by 4. And then you do the equation, and then you get $247. And then for B, the account pays 2.25% annual interest compounded monthly. So you have to divide that by 12, and you plug everything in, and then you get $2,294. And for C, the account pays 4% yearly. So you multiply that by 365 because that's a year, and you get $2,383.23.
Okay, so since we're coming over hang out, what are you doing this week? Oh, I thought Saturday is Mardi Gras. Oh, yeah, let's just go to that. Okay, I guess.
No, I don't.
See what way.
No, if you're gonna bring mine,
Yeah, that's what I guess.
Oh, no.
Saturday.
Yeah,
and
just
then-
like-
they would want Friday. What's she gonna do? Let's go with it. Home.
All right, ladies and gentlemen, in your packets, if you'll turn to section 7.2.
Hey, wait, you're pressing. I don't know what else it was. Oh, there's a weird dress on that website.
So today we're looking at exponential decay models instead of exponential growth models. So the graphs, instead of growing, will start up high and they'll go down and decrease. The equation is pretty much the same, it's just the number changes to make it decay instead of grow. So an exponential decay function is still the same form. So that a, b to the x, that's the form we're working with now. So an exponential function has an x as an exponent. That's what makes it an exponential function. Remember, these two numbers here, like pretend that there's parentheses around the b. The b goes to the x, or the x goes with the b. The a does not, so they can't be multiplied together because they're not like terms. A is a whole number by itself. The b is attached to the exponent, so you can't multiply them together, combine them together in any way. They're different types of numbers. The reason this one decays is specifically the b value. When that b is greater than 0 but less than 1, it's going to force the graph to go down instead of going up. So anything bigger than 1 makes the graph increase, but if it's less than 1, but it has to be bigger than 0, then our graph will go down. So it'll start up high, and then the graph kind of just falls and goes down. And that's because of this number here being less than 1. So instead of a growth factor, the b value is now called a decay factor. So that b, it just depends on the number that's in there, whether it's going to grow or decay. And the first two problems of your homework, you're looking at the equation and you're literally just saying it's growing because it's bigger than 1, it's decaying because the b value is less than 1. And it has nothing to do with a, it's the letter b. So the number attached to the exponent, that's the part that makes it go up or go down. Questions? So again, bigger than 1, it increases, it's growing, less than 1, but greater than 0, it's decaying.
Wait, why can't b be less than 0 again?
Having the negative number, that actually like flips the graph. Remember when we put a negative in front of like a parabola,
Oh,
it
yeah.
makes it go down. So it's more of a reflection of the graph, not making it grow or decay. Good question. Other questions? So if you look at the graph down below, parent function from Friday was the most basic function. Friday's graph grew. This one decays because now b is going to be between 0 and 1. So you can see that it does start up high. It's exactly the opposite of Friday's graph. And this one, it still will like horizontally go further. So that's the part to remember. Like it doesn't just stop, it just continues to like flatten out and go horizontally along the x-axis, never touching the x-axis. So if we look at the domain, Paige, what's the domain of this graph here? So the domain's still negative infinity to positive infinity. Just because we're changing the b value to be between 0 and 1 doesn't affect x. X can be any number, so you're allowed to plug any number in for x. How about the range? Ethan?
0 to
And parentheses around the 0, it's still an exponent. There's no way for it to touch 0. So it would be slightly above 0, which is why there's a parenthesis around there, and then to infinity. So we are going to graph one of the graphs on the bottom, and then we're going to flip and we'll graph another on the next page. But graphing is the same, so no calculator, doing it mentally by hand. So that means you should have fractions, not decimals. Do not rely on the calculator. Like the more you rely on it now, the harder it will be to convert for when you have the test and it's a no calculator test. So try and do everything mentally. The more we work with them now, the easier it will be. We're going to do them the same exact way. So plugging in numbers, -2, -1, 0, 1, 2, those same numbers we used before. We're putting them in for x. So no, you don't have to show your work, but for the first couple you might need to write something down so that you can kind of see what the exponents are doing to the negative numbers. So we have 2 and then a fourth to the -2. So what does a negative exponent do to a fraction? Sarah? Yeah, that's a good word. It reverses it, it flips it, it takes the reciprocal of it. But whatever number's in here, if it's to a negative exponent and this is a fraction, it literally takes that fraction and flips it. It takes the reciprocal, it reverses it. So instead of having 2 times a fourth to the -2, that's really 2 times 4 to the +2. They mean exactly the same thing. So it's taking that and flipping it, reflecting it, taking the reciprocal of it. So Sarah, 4 squared is
16.
times 2 is 32. So a negative exponent, when there's a fraction, it just flips that fraction around. The next one having the -1 power, so we'd have 1/4 to the -1, which is really just 4 to the +1. So a negative exponent, to make it positive, we take it and flip it. Well, that just makes 8. Virginia, when we have an exponent of 0, what does that do? It makes it 1. So if you have a 0 exponent, anything to the 0 becomes 1. So now that's 2 times 1, which is 2. And then we have 2 and then 1/4 to the 1. 2 1/4 squared. So Izzo, what's 2 times a 4?
A half.
Yeah. And then this becomes 2 times 1/16. 1/4 squared is 1/16. Anybody know what 2 times 16 is? Ethan? Awesome, 1/8. Any questions? So no, you don't need to show that, but it might help to write something down for you to kind of see. So when you're graphing this, then 32, that's obviously too high, so we won't graph that one. But looking at -1, we're going up to 8, which is just off the graph. And then at 2, 1/8 is a little above 0. So when you graph it, starting at the highest point, you can now see that those points are decreasing. Make sure that you continue your graph horizontally. Don't just stop at this last point. So continue the graph, make it skim along the x-axis. Questions? Sam, what would the domain of this graph be? So left to right.
Negative infinity to plus infinity.
Yeah, negative infinity to positive infinity. How about the range, Sam?
Negative.
So where does it start? Like
Oh.
looking from the bottom to the top. Where does it start? How high does it go?
0.
It starts at 0
Yeah, it goes to infinity.
and it goes to infinity. So when you're doing the range, always look at the bottom point and see how high it goes on the graph. Questions? So as I said, we're going to skip the graph right next to it. We're going to flip it over. And we're going to look at letter B's graph. So on Friday, when we graphed functions that had extra pieces, we said that extra piece meant it was translating, it was moving, it was shifting, it was sliding. So the +1 with the x, the -3 next to it, that's going to move our graph left, right, up, or down. We are not going to use those in the problem. We'll use that later after we have one graph. So you should have two graphs. Like for the last those three problems you're graphing, you should have had two graphs for those problems drawn. The original graph and then the translated graph. So the original problem that we're working with is just 3 2/3 to the x. So I'm eliminating the +1 and the -3. We're just looking at the basic graph. So 3 times 2/3 to the x. You're still going to use those same 5 numbers. And then if you need to write a little bit down so that you've got something to look at to know what's happening with the numbers, you can do that. So we've got the whole number 3 and then 2/3 to the -2. So what happens to 2/3 to the -2? How do we get that exponent to be positive? Ethan?
You flip it.
Yeah, so you're flipping that inside number. So now it's 3/2 squared. How do you square a fraction really easily? Paige? Oh, you weren't raising your hand.
No.
You were just moving it. Virginia? You square the top and bottom. So if a fraction squared, the top becomes 9, the bottom becomes 4. Square the top and bottom of the fraction. So now you have to multiply. Make the 3 over 1 if it makes it easier for you to multiply. So we're taking 3 times 9, which is 27, divided by 1 times 4 is just 1. Beginning of the year, I said you'd use fractions more this year than you probably have since 4th or 5th grade when you were introduced to fractions. And that's not going to go away. So hopefully working through them more, you'll get to be more comfortable with those fractions. Questions? So see if you can calculate the other 4 values.
Wait, so what's
So a negative exponent flips the fraction inside. So to the -1 really means you're taking 3 times 3/2, multiplying the top numbers. So now this is 9/2. So 3 times 3 is 9, bless you, and then divided by 2. When you plug in a 0, anything to the 0 power becomes 1. That should be the easy value, because it's really just the number in front, that a. Because an exponent with the 0 makes the number that it's attached to just the 1. And then we're dealing with 3 2/3 to the first. Anybody know what 3 times 2/3 is when you have a 1 there? H. So, yeah, that's just 2. And then the last one, we have 3 times 2/3 squared. So that means square the top, square the bottom. So we have 3 times 4 ninths. Ethan?
4 over 3?
Say again?
4 over
4 over 3. Yeah. Sorry, I just didn't hear you. Not that you were wrong. 4 over 3. Questions? So we're going to graph this first problem. I'm going to graph it just as it's listed. Does anybody know how we can estimate what 27/4 is? H? Yeah, so 27/4, what's the closest number that it's going to be? 6, because 27 doesn't go evenly, but 4 times 6 is 24, so we're pretty close. So she said it would be about 6. This is counting by 2s, it's going to be a little more than 6, so 2, 4, 6, and a little more. So -2, we're up above 6. 9/2 is 4.5, so at -1 to 4.5. At 0, we're at 3. 1, you're up at 2, and then at 2, we're at 4/3. Every single one of these graphs should end with that horizontal part. So make sure that you're like creating that curve to go a little bit beyond the last point that you graphed. So make it go horizontal a little bit. All right, so this is graphing it without any translation. Now looking at the numbers, how does the x plus 1 tell us to move the graph? Paige?
Left 1 and down 3.
Right, so this part here moves the opposite. Even though it says plus 1, that's the h value. It really moves to the left. And that part makes it move down. So we're taking the 5 points that we just graphed and we're shifting them. So we're going left 1, so the left point is going to move left 1 and then down 3. Now make sure that when you're counting down, like when we're moving left 1, this is counting by 2s. So left 1 and down 3. It's a little harder when you're counting by 2s. So left 1 and down 3. My graph should go down a little bit more yet. So you'll have a big enough graph tonight where you don't have to worry about counting by 2s. The domain's going to be negative infinity to infinity. What part of the range, or what part of the equation helps us determine the range? Yeah, that k part. So the k helps us determine the range. So k is negative 3. So the range will be from negative 3 to infinity. So k is what determines your range value. Question. So the graphing is almost identical, but the graph goes down instead of growing up. Try and use your mental math instead of relying on the calculator. At the bottom, we're going to look at just like a word problem as to how we can apply this to some information besides just relying on the graph. And this equation, it's pretty much the same as what we talked about on Friday. So they're exactly correlated. It's just one number makes it go up, the other number makes it go down. So real-life quantities can decrease by a fixed percent. If you have a value of something, what would decrease in value in our world today? Cars decrease in value. What else decreases in value? Sam?
Video games.
Yeah, any kind of technology decreases in value. So anything you buy, pretty much the next day, you try and take it back, and it's a technological device, it's not going to be worth whatever it was you bought it for. Unless something's wrong with it, they'll generally charge you a restocking fee. So the equation looks almost identical to the growth model. So we have an A, it's 1 minus r to the t. Anybody remember what the A stood for on Friday in the word problems? Sarah?
The initial amount.
Yeah, that was the initial amount. So that's how much it costs when you buy it. What's the R? H.
The rate.
Yeah, that's the rate, and that is as a decimal. Why is it a minus in here instead of a plus? So think about, why would it be minus, Sam?
I don't know.
Maddie, why do you think it would be minus?
Because it's decreasing, not increasing.
Right, it's decreasing, so it has to be less than 1. So we start with 100%. We're not increasing, we're not adding more to it, we're decreasing that value. So that's our decay factor. So that number is going to be less than 1, not more. So we're gonna do just the problem at the top of the next page. Tomorrow we'll come back and finish some of the notes. But if you look at the top of the next page, it talks about a TV. So a new TV costs $1,200. Doesn't tell us what size TV or what kind, but $1,200 for the TV, probably a decent TV. The value decreases by 21% every year. Right, an exponential decay model giving the TV's value Y in dollars after the number of years, how many ever years we're looking at. And then the next part says estimated after 2 years. So the first thing we want to do is to try and come up with an equation. So instead of adding, we're decreasing, we're subtracting that amount. So Ryan, what's our initial value for the TV? 1,200. What's it decreasing by?
1 minus 0.2,
Right, so 1 minus 0.21 is?
21%. So, 0.7.
Yeah, good. So 21%, 1 minus 0.21 would be 79.79 or 79%. So that's the value left on that TV after a year. That gets raised to the exponent of t, because it could be any number of years. So that makes it an equation once we have that t there. So now, once we're dealing with these equations, you're going to need that calculator. So we have 1,200.79. How much is it worth after 2 years? So in your calculator, we have 1,200 and then 0.79 with the squared exponent. Sarah, how much is our TV worth now 2 years later? So 2 years have gone by. TV's now only worth $742. So you lost like $450 off that TV for 2 years. Bridget. Yes, a half-life. That's what, carbon dating half-lives? Tyler?
Should be 70.
48.
Yeah, I wasn't saying anything, but I
Oh, I'm sorry. You should have. Thanks, Tyler. All right, so if we were to look at the next one, we would have to use the calculator and that table function in the calculator. We could figure out how many years it would take for us to get like $300 out of the TV. Homework tonight. This is really important. I didn't give you an assignment sheet. The homework is for Friday. So if you look at Friday's assignment, that's the homework that is listed. It's book homework again. And there's like 7 or 8 problems there. So volunteer for 31, page Sam 32.
Oh wait, I'm doing 31 or I'm doing 32?
You're doing 32 now. Have an awesome day.
Oh, I think.